Hi everybody. Now that we've studied the atom and we know the three subatomic particles, we can take a closer look into the nucleus of an atom to describe unstable nuclei and understand what radioactive decay is. So first, let's start with the scientific definition, and the scientific definition of radioactivity. This is when you have emission of high energy radiation or particles from the nucleus of a radioactive atom. So what that means is that in this atom over here, if this is the nucleus, what we'll see are particles and radiation, basically energy slipping out at a constant rate. That's radioactivity. Every element greater than atomic number 83 is considered radioactive. So if you go to the periodic table and you find the high numbered elements, there's a good chance that they are going to be radioactive. When this radiation is given off, there can be changes to the nucleus. If it's a particle the nucleus is losing, it might be a crucial particle like a proton or a neutron, and that might have some severe changes because it has happened. For example, by losing protons, that can result in different elements being formed. Now, an example of that would be uranium. If I am an atom of uranium and I lose 2 protons, what element am I? So to answer this question, all you have to do is get a periodic table out and we'll locate where uranium is. And if you take a close look, you'll find it at the bottom, an F block, and it has an atomic number of 92, which means it has 92 protons in its nucleus. If it loses 2 of those protons, it then has 90. And 90 protons is the identity of thorium. So by losing 2 protons, by having them slip out of the nucleus, you can go from being uranium to thorium. Atoms with 84 or more protons will have particles or energy slip out at a constant rate. This process is called radioactive decay. If we want to take a look at what that would appear like, here we have a nucleus which is jammed full of protons and neutrons, and we see a particle slipping out. This happens to be called an alpha particle, and it's made of 2 protons and 2 neutrons, and you see that it has left the nucleus, and now it's going to go elsewhere. So let's take a moment to review a little. I'm going to put this set of blanks up there, and if you want to go ahead and pause and take about 30 seconds and see if you can fill in the blanks here with words that we've learned here in Chapter 4. And if we know these ideas, it's going to help us understand the rest to come in 4.4. Go ahead and pause. Okay, let's fill in those blanks. So isotopes then are atoms of the same element that differ in number of neutrons. The number of protons does not change. If it did, you would have a different element. Remember that the number of protons guarantees an element's identity. So when the number of protons changes, so does that element. Okay, so we have to look at 3 different types of radiation that exist. The first type of radiation is called alpha radiation, and it consists of 2 protons and 2 neutrons. So there's a total of 4 subatomic particles that are released as an alpha particle in alpha radiation. When an alpha particle is emitted, the atomic number decreases by, and since it loses 2 protons, it must decrease by 2. So if we take a look at it, we saw this picture a minute ago. Here's the nucleus. It loses 2 protons and 2 neutrons, decreasing the number by 2. So therefore it will change elements. It will go down 2 elements from where you originally started at. Now, a beta particle is given off during beta radiation. And it's emitted when a neutron decays into a proton and an electron. The beta particle is actually the electron that's emitted from the nucleus. Therefore, the atomic number of the element will actually increase by 1. Let me show you why and how that works. Okay, so if we have a neutron, a subatomic particle, break down into two different things, a proton and an electron, the electron is going to go ahead and it's going to leave the atom. But now the neutron has changed into a proton, which means that whatever atomic number was there before now has gone up by 1. So atomic numbers during beta radiation, when you emit a beta particle, will cause it to increase by 1. And the last type of radiation is called gamma radiation, and that gives off gamma rays. These are very penetrating, high energy waves. They're electromagnetic, they don't have mass, they don't have charge, and they travel very quickly at the speed of light. And they're going to be released whenever you see that alpha or beta radiation occur. So what that looks like is this. So here you see a wave of energy and not an actual particle being given off. And that's the essence of a gamma radiation. Okay, each of those types of radiation and particles has their own symbols. So let's go ahead and take a look at what those are. And an alpha particle is going to look like this. We're going to use a nuclear symbol for it. It's going to be 4/2 He. And since we're aware what nuclear symbols are and how they're arranged, the mass number is over the atomic number. And if you subtract these two, that gives you the number of neutrons. So we can see that there's 2 protons, a total mass number of 4, which means 2 protons plus 2 neutrons. And this is the symbol for alpha radiation. Here's a particle. It's very large and very slow. And a piece of paper can actually stop it. So it's not so much the alpha radiation. If you remember, during Rutherford's experiment, he shot alpha particles at gold foil, and 90% or better went straight through the gold foil because it was cut very thin. So these are large, slow particles, but if you have something as thick as a piece of paper, it can stop one of the alpha particles. Second, we have the beta particle, and its symbol is going to look like this. You're going to have 0 over -1, and then you're going to have the beta symbol. Okay, put a little stem on the bottom of the B there. Okay, so what that means is that the mass number is 0 because it's an electron that's emitted, and we use the -1 to kind of display the fact the electron has a negative charge. This one is a little bit more penetrating than the alpha particle, and this one can be stopped by aluminum foil. The last symbol for a gamma particle is going to look a little bit different. It's going to be 0 over 0, and then we have the symbol gamma. And gammas, we said, are very penetrating. They're high energy, and sufficient quantities of any material can stop it, but most common we use lead. So think of when you go get x-rays done of your teeth or your head, they're going to put a lead vest on you because they're trying to stop the gamma rays from penetrating through your vital tissues. However, if you looked on the outside of a nuclear reactor, what you would find is thick walls of concrete, which can also stop the gamma radiation. Okay, so that brings us to figuring out by looking at pictures what type of radiation that we're looking at and how do nuclear equations factor into the whole thing. So here we have some sort of nucleus that has 88 protons in it, a mass number of 228, and the element is radium. And we can see that something is given off here. And what we're left with then is this nuclear symbol. We have a different element, actinium, and it has an atomic number of 89. So what we see is that the atomic number has gone up by 1. Mass number stayed the same, and we have to think which type of radiation displays an increase in atomic number, and that it would be beta radiation. Down here in this example, we see radium with 88 protons and a mass number of 226. And in the next, after the arrow, in the after scene, we have mass number of 222, which means it went down by 4, and we see an atomic number of 86, so the atomic number went down by 2. And kind of the dead giveaway here is this symbol right there, which is alpha radiation. Here's the particle. And we know that because the atomic number's gone down by 2, mass number goes down by 4, and it's absolutely typical of an alpha particle radiation. So this would be alpha. Okay. Now, the other thing that I just want to mention is the fact that we don't forget about the law of conservation when we look at nuclear equations, because if I go ahead and I add these two together, 222 plus 4, that gives me the 226 on this side here. So the two of these together, nothing was lost that we can't account for. Here we started with 88, and if we look at the alpha particle that flew away, it had an atomic number of 2. And what's left over here is the 86. The two of those together are equivalent to what you started with here. So we are still conserving the law of conservation even during a nuclear reaction. So I hope this helped you understand section 4.4 a little bit better. Read that textbook, answer the section assessment questions, and it should all fall into place. I'll talk to you next time. Bye.